There you go. All right, where on the formula sheet? Do you remember where all those formulas were?
The third page. No.
Page 4. So all your thermo formulas, page 4, your temperature equations were on page 3. So this equation is on there, and then what they mean, so Q is energy transfer, and it's always going to be joules. M is the mass of the materials, it's always going to be in kilograms. C is the heat capacity. You will always be given heat capacity. You will never have to do that on your own. And then delta capital T is change in temperature. And then the other equations on there, P equals Q over delta little t. P equals K times A times delta capital T over L. And then K equals P times L over A over delta temperature. So what does all that mean? P is the rate of energy transfer, is always in watts. So like your light bulbs, that's what watts means. So if you have a 40 watt light bulb, that's what that means. It's transferring that much energy. Q, we just talked about with energy transfer. Delta little t is change in time. So delta big T is temperature, little t is time. Always, always, always in seconds, not hours or minutes or days. Or so if they give you like something in an hour, you got to change it. K is thermal conductivity. A is the area of what you're talking about. And then L is how thick something is. Good so far? Kinda? All right, we're gonna switch now. So we're calculating the energy transferred when a block of aluminum at 80 degrees Celsius is placed in 1 liter or 1 kilogram of water at 25 degrees Celsius. If the final temperature is 30 degrees. So we're figuring out what is the amount of energy that's transferred. So once you get really good at these, you're not going to have to do all of these steps, but we're going to do all of these so you see where things come from. So what's the mass of the water? 1 kilogram. Remember I told you you'd always know heat capacity? They didn't tell you up here. I'm going to tell you right now. It's 4,184. And the unit for this guy is joules over kilograms times Celsius. But let me give you a hint. We're not going to, when we start calculating this, all those units go away. So you're not ever going to do anything with this. What's the change in temperature? Well, first off, let's talk about which one. Let's talk about change of temperature of the water first. Since we talked about water here. What's the starting temperature of the water? 25. And what is it going to get to? 30. I don't ever want a negative number here. That's why I did it like that. I can try to make that bigger. Doesn't matter. And so my change in temperature is 5 degrees Celsius. Then the heat capacity of aluminum is 900. And the unit, again, you're not ever going to have to do anything with this, but I want you to see it again. And now my change in temperature for the aluminum. What's the aluminum starting at? 80 degrees Celsius. And what's it gonna get to? 30. So my change in temperature is 50 degrees Celsius. We good so far? Yes, ma'am.
Where did the 900 come from?
I gave it to you. You'll always know those. Yep. So one of the things I don't like about Project Lead the Way's PowerPoint, they don't ever tell you that anywhere. And numbers just start showing up. And the first time I ever went through this, I kept going, I get where this stuff was. We good? All right. So I gave you this part. What are your unknowns? So what are we trying to find out? I don't know the energy transfer. So that's my Q. And I have no idea how big that aluminum block is that's in that water. So that's the mass of the aluminum block. And I should have covered this up. So the equations, that's that Q equation. Q equals M times C times delta temperature. And if you remember from Wednesday, energy transferred from one object to another, it means the energy is the same for both. So in this case, this aluminum block is going to get colder to get to equilibrium, and the water is going to get warmer to become equilibrium. So the block is going to lose energy, the water is going to gain energy, and the amount the aluminum loses is the same the water gains. That makes sense? So that's what this means here. The energy transferred from aluminum is the same as the energy transferred for water. That's what that means. So now we gotta solve. I'm gonna start plugging. So Q of water equals, what's the mass of the water? 1 kilogram. All right, I'm gonna tell you now, I'm dropping all of my units because based off of first block, they started getting really confused with the units. And we're gonna drop them anyway, so I'm just not gonna write them, but know that it is kilograms. What was the heat capacity for water?
900. Oh.
Yeah, that was the 4184. And then what's the change in the temperature of the water? 5 degrees. 5 degrees. I'm just gonna leave it at 5. And all you do is you multiply them. What's the number?
20,920.
There you go. 20,920. Does this have a unit? Joules. Capital J. That's it. Well, that's it for that. We have one more stuff, but. Are we good for me to flip? All right, so remember we had, if I go back real quick, I solved now for that unknown. This is what I still need to solve for, is how big is that aluminum block? So remember, Q of AL, or the energy transfer from the aluminum, is the same as the energy transferred for the water. and that was 20,920. You didn't really have to write that down, just, I flipped to a new page, so I like to. So with that being said, this is the equation I'm gonna use. I'm only dealing with aluminum right now. I dealt with the water. So the energy transferred from aluminum equals the mass of the aluminum times the heat conductivity times the change in temperature. And you just start plugging. So my energy transferred is 20,920. Again, I'm gonna drop the units. What's the mass of the aluminum?
1 kilogram.
You don't know.
I don't know that one. That's what I'm solving for. Trick question. What's the heat capacity? 900. And then the change in the temperature was 50. Yep.
That number.
45,000.
Yeah, 45,000.
I am going to, what I'm gonna do, and there's multiple ways to get there, I'm just gonna show you. I'm gonna take these and go down a little bit further. What's 900 times 550?
45,000.
Yeah. So I'm gonna leave it, just so you see where I'm going. And then from here, I'm gonna divide by 45,000. So that these guys cancel out. Ends up being 0.46.
5. It's like 40.
What unit is that in? I guess we should know
Kilograms.
this. Kilograms, you're right. So that aluminum block is 0.46 kilograms. So it kind of makes sense now why the equilibrium temperature was what it was. Just for fun, what is this in grams?
4,600.
460. Just because I would not put it past Project Lead the Way on the EOC to have a problem like this, and they give you all your answers in grams. They're tricky like that. So. But again, this is in your formula sheet, so you can figure it out. But we good? Not too bad? Alright, so we're going to look at a wall. And we're going to calculate the energy transfer in a wall section that's 2 meters by 1 meter. And then the wall's 0.04 meters thick with a thermal conductivity of 0.1. And then you got that weird funky unit. Opposing sides of the wall have a temperature of 10 degrees Celsius and 5 degrees Celsius after 1 hour. So it means after 1 hour, one side's gonna be 10 degrees Celsius, and the other side's gonna be 5 degrees. So let's list our values. What do we know? What's the area? 2 what? That wall is 2 meters by 1 meter, and when you multiply, you get 2 meters squared. What's my thermal conductivity? Bless you.
0.1.
Yeah. And then that weird. And then the wall is 0.04 meters thick. What's the difference in temperature?
5 degrees.
5 degrees. And how I got that? One side of the wall is 10 degrees. The other side of the wall is 5 degrees. So it's 5 degrees different. And what's my change in time?
An hour.
It's an hour, but
3600.
remember, it's always in seconds. So you'd need to do 60 times 60 in this case. Because if you plug, let's say you leave it at 1 hour and you go to plug that one in later, it's not gonna work out right. Are we good? I am gonna cut these. All right, so my unknown values. I have no idea at what rate this energy is transferring. Remember, that's shown in watts. That tends to help people. And I also have no idea how much energy was transferred. So I don't know the joules. So I'm going to use a P equation. So if you remember that one. What's the problem though with this equation?
You don't know.
I don't know two of them. I don't know P and I don't know Q. That's why if you remember that one slide had two P equations, you need both of them. And it will make more sense in a couple minutes why we need both of them. Or how they work. And so to make things simpler, we're gonna move this equation around to solve for Q. And all we're gonna do is do the Q equals P times change in time. So all I did was multiply change in time here times here and then flipped it to make it pretty.
And I just went ahead and solved those, like I solved P, then I solved Q.
You can do that too. So I'm going to show you the absolute longest, not always the longest way, but most of the time the longest way. And there are going to be other avenues to get there. But there are some people that need to know exactly where everything comes from. And then we're gonna combine these equations, right? So I'm gonna solve for Q. This P, I'm gonna plug this equation into it. So it's gonna be Ka times change in temperature over thickness times change in time. Ooh, there you go. So now you can see why there's two P equations. This is the worst part about this particular problem, is getting to this point. Because from here, we're just plugging and you're gonna solve. So you're through the worst of it. Am I good to flip? Because I know some of y'all are working ahead, so I don't know if people are writing or. All right, so now we're gonna go in. You don't have to rewrite this equation. I am, just because I went to a whole new page. All right, so Q equals, what was K? What did K stand for? Thermal conductivity, and what was it?
0.10.
Again, I'm gonna drop my units, so it's gonna be 0.1. And what was my area?
2.
2. And change in temperature? Let me put a 0 here to make that look less confusing. Or I can even change it with the old school times. And then what was the thickness of the wall?
2 meters.
No, the thickness, 0.04.
0.04.
And then change in time was 3,600. So if you hadn't changed it to seconds and you left it as hours and plugged a 1 in here, it would be.
It's
And then you just solve it. Josh, what'd you get?
P is 25, or that first part is 25, and then Q is 9,000. Is that right?
How much?
P is 25 watts, and then Q is 9,000.
Close. Think about just Q for now. Q is real close and kind of 9,000. 90,000.
Yeah, no, I still don't remember. I wrote that one.
I thought that was probably. And just so that I make sure we're all good, how we got to this 90,000, 0.1 times 2 times 5 is 1 over 0.04 times 3,600. That's how you get it here. So the amount of energy transferring through this wall is 90,000 joules.
So we'll always have these equations given to us.
Absolutely. I never make you memorize an equation. The real world is not like that.
Tell us one day. Tell us this, yeah.
But don't tell your math teacher that I told you that. We do real world math in here.
This is actual math.
Are we good? We're almost done. I'm gonna flip back to the PowerPoint. You can see why now I don't like their PowerPoint. Very confusing to me. All right, so we're gonna talk about U value versus R value. All U value is the coefficient of heat conductivity. So how well does a particular material conduct heat? You will never have to solve for this one here. If you go to college and major in engineering, you're probably going to have to, but in here, you're not. It's always going to be given to you. So that's a funky looking, you're not going to ever have to know that. So pots and pans, they're measured in U values. Anybody ever heard of BTUs? In the US, we do a lot of our measurements for U values and BTUs. So like if your parents go buy a heater or you go buy a heater and it's measured in BTUs, that's what it's doing. The higher the number, the better it is at conducting heat. And then the R value is how well does a material insulate or resist the heat. Again, you're going to be given the R values. You're not ever going to have to calculate the R value. You're going to be given it. All right, so let's look at a house. And we're determining the R value at the wall cavity. So the wall cavity is through this part here. These down here are two studs. So these would be like the studs in your floor. So that, just know the difference between them. So again, the R values are given to you. So a brick has an R value of 0.8. And then there's a little gap here, and this is true in your house now. There's a gap between the outside of your house and the inside insulation part. So you have 1 inch of airspace, then you have 1 inch foil face poly, If you go to Lowe's and you've ever seen big old sheets that looks like kind of like aluminum foil with styrofoam in the middle, that's what that stuff is. That has an R value of 7.2. Fiberglass in there has an R value of 19. And then your drywall, which you have inside your house, is 0.56. So you gotta determine what's the R value. You ready? You add those numbers up. So 0.56 plus 19 plus 7.2 plus 0.17 plus 0.8. Do not include your studs. We'll talk about those in a minute. You just add them up. No fancy equation. Nothing like that. So based on rounding, you're going to get around 27.7. What do you notice is missing from R values? Units. There's no unit for R values. The higher the number, the better your house is as far as resisting heat. This is a pretty typical number for houses.
Is it the same for keeping heat in, or is it
Both,
It's like
yeah.
insulation.
Insulation, yeah. And that's why most houses have fiberglass in them, because they're really good at their job. We're working with fiberglass right now in aerospace. And you know never to touch fiberglass. So yesterday I panicked because I knew I had fiberglass laid out for aerospace yesterday. And luckily Mr. Schmidt came in, and because I could just see somebody coming in and grabbing it, and it was not a big deal. All right, so that was at the wall cavity. So now at the stud location. So we're worried about down here.
We saw that. Why can't you touch fiberglass?
There's little shards of glass all in it.
Oh, okay. Is that like the Pink Panther stuff?
Yeah.
So
Is that like
I don't know. It's in plastic. Actually, right after lunch, I'll show you this.
Okay.
I'll put gloves on and stuff. So at the stud location, these are my studs. What is it's studs instead of what? Fiberglass. So you're gonna do the same thing, but instead of using 19, you're gonna plug in 6.88. And based on rounding, you probably got around 15.6. This is why your floors are colder most of the time in the winter. They're not as good a job of insulation and keeping your heat. And that's it.